Our next topic is about 2D NMR. We will start with methods and principles, and then in the following slides, we are going to talk about different 2D NMR spectra. As we all know, 2D NMR spectra can be homonuclear or heteronuclear. And an experiment may have more than one channels involved. Each channel pulses nuclear spins with different pulse sequences in different NMR frequencies. Homonuclear spectroscopy can be done with one channel. Heteronuclear NMR requires simultaneous manipulation of two species of spins that have different NMR frequencies, and hence an extra channel is required. Many experiments also manipulate the spins with gradient pulses for different purposes, which requires an extra channel to create gradient pulses. Here, we introduce only a basic pulse sequence for a 2D NMR experiment, which contains 4 segments: a preparation segment, an evolution segment, a mixing segment, and an acquisition segment. The preparation segment is often a time delay for all spins to completely or partially relax back towards the equilibrium before the next pulsing sequence starts. The evolution segment allows nuclear spins to dephase to different degrees before they are pulsed for the next segment so that a 2D spectrum can be constructed. During this segment, the delay time T1 gets sequentially increased between 2 sets of pulsing, including data acquisition. The mixing segment is to manipulate nuclear spins for different kinds of controlled spin-spin interaction so that different NMR spectra can be obtained. The acquisition segment is simply for the receiver to collect a set of 1D relaxation data in T2 domain for different experiments. Each set of the FID contains n data points. N is usually quite large, say 2048. Note that 1D NMR data are called FID, short for free induction decay, which comes from the fact that NMR data are decaying signals induced to the receiver coil. If you look at a 1D NMR data folder, there is a file called FID, called FID. If it's there, the binary NMR data are stored. After data collection, the next round of exactly the same pulsing sequence then starts with a different T1. Remember where we introduced T1? T1 happened in the evolution time. In other words, T1 is the evolution time. Say this looping procedure is repeated m times. Then we have a total of m 1D FIDs. Each of them is a function in T2 domain, denoted here as Fi T2. I from 1 to etc. to M, each of which is related to a different TI, because we use different TIs for different rounds of pulsing. Here the number M is usually quite small, say 256 or even smaller, 128. How NMR data are processed. The first step is transforming all lowercase f's or all fi's in the T2 domains into 1D spectra. Each of them fills a column of a 2D matrix, i.e., a total of M Fourier transforms in T2 are performed for all FIT2. In the end, only M columns of the matrix is filled. Because we got only M FIDs. To expand the matrix, we fill the empty part of it with zeros so that it becomes an n by n matrix. Then each row of the matrix forms a 1D FID in T1 dimension, denoted here as GJ-T1. Now it's row. Previously it was column. And finally, a total of n Fourier transforms in T1 are performed for every row of GJ-T1 to form a 2D spectrum in frequency domain. One of the most commonly used 2D NMR spectroscopy is COGI, simply short for the correlation spectroscopy. It was the first 2D NMR spectroscopy proposed in NMR history. The inventor was a Belgian physical chemist and physicist, Jan Giner, who presented the idea verbally at a conference in 1971. The first experimental demonstration of this technique was, however, carried out by Richard Ernst. As you can see on the screen, the pulse sequence is very simple. A preparation segment, an evolution segment, and an acquisition segment. There is no mixing segment because COGI only collects spin-spin coupling information which has been achieved in the evolution time without the need for an extra spin-spin mixing. A COGI spectrum shows through-bond correlations of protons that are usually 2 to 3 bonds apart, which allows the assignment of neighboring protons. For example, the correlation between the CHs in the graph on the right can be easily observed in a COGI spectrum because they are either 2 or 3 bonds apart. COGI is also the most intense NMR correlation we can obtain and is widely used for molecular structure determination. Often, weak 4-bond coupling can be observed, especially when there is a double bond involved. On the screen is an expansion of a 2D COGI spectrum. As you can see, correlated 1D spectra are shown on the sides of the spectrum. Because it is a homonuclear 2D spectrum, the images of the off-diagonal cross peaks are symmetrically distributed about the diagonal line of the spectrum. In this case, a cross peak and two correlated peaks on the diagonal form a right triangle. The dashboard in the spectrum shows two bond proton-proton correlations between the protons of a CH2 pair. The arrow shows 3 bond proton-proton couplings for 2 H's across 2 carbons. A very useful NMR spectroscopy is TOCSY, short for Total Correlation Spectroscopy, also called HOHA, short for Homonuclear Hartmann-Hahn Spectroscopy, where Hartmann and Hahn are the names of 2 American physicists who first proposed the idea of spin locking in 1962. TOCSY is similar to COGI, in which not only the cross peaks for directly coupled nuclei are observed, but also those between nuclei that are connected by a chain of couplings. This makes it useful for identifying the larger interconnected networks of coupled nuclear spins, which is achieved by inserting a repetitive series of pulses that cause isotropic mixing during the mixing period. 2 different pulse sequences are shown on the screen. Typically, there is a train of pulses in the mixing segment, which consists of a sequence of repeated spin echo pulsing modules to lock the spins onto the XY plane so that long-range coupling correlation of protons can be observed. As he said, TOCSY shows through-bond correlations of protons that can be multi-bonds apart, as shown on the right figure, where the multi-bond protons are changed by carbons. In fact, it can also correlate all protons changed by nitrogens and/or carbons. Now, we want to introduce a concept called TOCSY spin system, which is a group of protons changed by carbons and/or nitrogens. For example, all the protons in the bottom right graph form a TOCSY spin system because they are changed by carbons and a nitrogen. Non-protonated elements, such as quaternated carbons, break the chain of a TOCSY system. Therefore, any protons beyond the COs in the figure are not in the TOCSY spin system, and hence no TOCSY correlations with them can be observed. A TOCSY system appears to be a lattice of peaks in a spectrum. As you can easily see from the spectrum, there are 2 TOCSY spin systems for 2 ethyl, 1 indolent. In other words, given a spectrum like this, we know immediately that there are 2 TOCSY spin systems in the molecule. TOCSY mixing time plays an important role for the observation of a toxic system. For short missing time, for example 20 to 30 milliseconds, only Koji type of correlations can be observed. A longer isotropic mixing time causes the polarization to spread out through an increasing number of bonds, and hence, for long mixing time, correlations between more distant protons can be observed, which allows us to identify all changed protons within a toxic spin system. For example, setting mixing time to be 110 milliseconds can correlate the H1 to H6 in a carbohydrate molecule. Toxi is particularly useful for peptides and protein NMR assignments because the toxic patterns of all common amino acids are known. We have talked a lot about NOE. Let's now focus on a similar kind of spectroscopy called ROGI, short for rotating frame over Hauser enhancement spectroscopy. Both NOGI and ROGI show through-space correlations between nuclear spins. They allow us to work out the distances between nuclei and hence 3D molecular conformation. As shown in the top right graph, depending on the molecular weight, the NOE values can be positive or negative. ROGI, on the other hand, is always positive. Therefore, it is better for a situation in which the NOE is too weak to be detectable, usually due to the molecular weight around 1,000 daltons. Both of them give us the information of NOE cross-relaxation. But the irradiation techniques they use are different. If you look at the basic NOE pulse sequence, the continuous wave, i.e. a long duration pulse, is applied before the 90-degree pulse P1, which means that it is used to irradiate the M naught that's aligned with B naught. In other words, it irradiates MZ. Therefore, the signal acquired after applying P1 contains the cross-relaxation information of the Z magnetization. ROGI, on the other hand, rotates M naught from its equilibrium orientation onto the XY plane and then spin locks the MXY with a train of spin echo pulses for the NOE to take place. Therefore, the signal acquired contains the cross-relaxation information of MXY. In fact, ROGI pulse sequence is the same as that for Toxi, but with a much longer mixing time, for example, 250 milliseconds. For this region, weak ROGI peaks can sometimes be observed on the Toxi spectrum. Now, we want to talk about HSQC, short for Heteronuclear Single Quantum Coherence Spectroscopy, which is another very useful NMR spectroscopy. It shows one-bond correlation between 1H and less sensitive nuclei, or vice versa. The application of it is straightforward, i.e., it allows us to assign protonated nuclei after the protons attached to them are identified. Differently from many people's understanding, it actually collects the proton signals that contain the information of 1H spins that are precisely manipulated to correlate with protonated carbons, and hence provides us with strong NMR signals because they are 1H signals, not carbon-13 signals. It can even be edited so that the CH2's CH correlations appear to be negative, which can then be displayed in different colors. In this way, it helps us quickly identify CH2 pairs that are attached to the same carbon. This feature is extremely useful in NMR spectral assignment, as will be explained later. Often, we don't even need depth or APT if we have HSQC, because HSQC not only provides all information we can get from depth and APT, but also the protons attached to them. It is a 2D spectrum, often capable of separating or clarifying 1D proton peaks that are overlapped in 1D spectrum. And lastly, 1H13C HSQC spectra are usually optimized to observe peaks that are correlated with spin-spin coupling constant around 140 Hz, which can be changed to observe those correlations for any spin-spin coupling constant. We only need to change a parameter for it. For example, if you have a molecule that have a particular Hc coupling with coupling constant of 250 Hz, we simply change that parameters to 250, then it will work. Now it's about HMBC, short for heteronuclear multiple bond coherence spectroscopy. It shows multi-bond couplings between 1H and less sensitive nuclei species, as shown on the right, where the pink curves indicate the HMBC correlations that can be observed. Again, it also collects the proton signals that contain the information of 1H spins that are precisely manipulated to correlate with all kinds of carbons, and hence provides us with strong NMR signals. Therefore, it allows us to assign non-protonated nuclei, for example, quaternary carbons or carbonyl carbons, using the correlations with their neighboring protons. Note that HMBC is optimized to observe multi-bond couplings around 8 Hz, which is usually the case for most long-range 1H13C couplings. There are two facts worth mentioning here. One, Two bond couplings within aromatic rings are often not observed. 2. One bond couplings around 140 Hz can often be observed as a 2D doublet. We will talk about this in details later, because I need to show you the example for this so that you can easily understand it. This concludes my lecture 5.